I know how to open it.
Where is it?
In there.
This one? Let's get jolly.
Don't close it tight. Mom, you close it tight.
It's rice up on the stove.
I had it.
Just heat up.
Okay, so let's get started. Again, sounds pretty good. You got the earbuds in, and I know if you don't use earbuds and you play it loudly, your mic on the computer will pick it up, and I'll hear myself talking, and it just gets crazy. So hopefully you can hear me, and let's get started with that worksheet. Hopefully you printed it out, and Matt's going to be my portal to you guys. So if you got a question, tell me to stop, those kind of things, and Matt's here today. It's good. So let's get started, and if my 4-year-old chimes in, hey, that's just how it works. I'm using his headphones, so they don't really fit, but you get the idea here. Somebody has no... Okay. Any case, let's get started. And here's Brady. Say hi, Brady. You're not feeling well, right? Say hi. Hi. Hey. All right. Any case, let's get started. And I'm going to share my screen now. And we're going to go to that worksheet, and we're going to use formal charges and screen share. And I'm going to go to this. Okay. And I'm going to clear this entire sheet. All right, here we go. All right. And it looks like I might have to redo this because it's not giving me the extra. Here we go. Yeah, I'm talking. Now we've got some issues here. Let me reload it again, I think. Bonding 3 and illustration. Okay, good. Here we go. So we're going to start with ClO -1, and we're going to write the Lewis dot diagrams, not so thick, I guess. And we're going to put to use all the things you've learned up to this point. Hopefully, it's going to make some sense for you. And this is a polyatomic ion. And one little clue with the polyatomic ions, they cannot be polar. So it's a question that's going to be non-applicable because the entire cluster of this grouping is going to be -1. All right, so let's start with the Lewis dot diagram. And again, we're going to employ the our helpful tool of formal charges to help us draw these structures and find the best probable structure here. So here's chlorine, and it has 7 valence electrons, so you write that. All right. And I draw my 6 valence electrons. Then I have my oxygen. And I draw the 6 here. Okay. And the 6 dots go here. And now I'm going to move them to make one bond. So I put 1 here and I put 1 here. All right. And then, as I've been telling you all these years, evaluate your scenario. So I had 1, 2, 3, 4, 5, 6. I'm just making sure I have the right number of valence. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yeah, I'm missing an electron here. Okay, that's what didn't feel right. Okay, so if you notice, I put my 7 valence electrons for the chlorine, and I have my 6. And what I did is I made one bond. And if you remember, last year we evaluate this structure just quickly by stability. Chlorine has, by sharing, has 8, and then oxygen by sharing has 7. So the octet rule is not satisfied for the oxygen. So it needs 1 more electron from the environment. I'm going to draw that as a triangle. So this oxygen is going to absorb an electron from the environment, at least that's what I'm going to say it does. Oh, I see the problem. Okay, let me X this off. I'm sorry. Thanks, Matt. Let's fix this. Let's fix this. Okay. Thank you. I'll start again. Bad Grotsky, good pizza. That's why I need the eyes in the classroom. Thank you, Matt. All right, so let's share the screen here. And I want to share the right screen. I was sharing the wrong screen. All right, hold on, party people. All right, hold on. Hold on, fix this quickly. Get rid of that. File, new on background. One more time as the song goes. One more time. Yeah, you didn't want to hear me sing this morning. Let's see. What was the name of this thing? This was the name of. I'm in the wrong thing here. Okay. Hold on. Bonding, chlorate geometry. Okay. All right, let's go back to where I was. And screen share. And right there. Okay, Matt, I need you to tell me if you're seeing the problem. Are you seeing this? Are we seeing that? All right, so let me start again. Sorry. Okay, and it's a good thing we have the ears in the room. I just kept going. All right, so back to business here. We have chlorine. It has 6 valence electrons. It has 7. Okay, I can do this. And then we have the oxygen, who has its 6. So 1, 2, 3, 4, 5, 6. And to evaluate, this chlorine is satisfying the octet rule. So it's stable. It's filling that 8. And oxygen with 6 valence electrons, using the one from the chlorine and sharing, only is feeling like it has 7. It wants to have that 8 to be as stable as its noble gas counterpart. So what we say is that this one absorbs an electron from its environment. I'm going to draw that electron as a triangle. Now, what I will say is you can't fall in love with the idea that, hey, the red dots belong with the oxygen, the blue dots belong. You put out all the dots. Now, remember, electrons are not dots. They're waves. So we're using these dots as point charges to make some sense and predictions based on what these structures will have with its properties. So there's a limitation to this, and we're going to run into it today, hopefully, if you can see it with me. All right. All right. Now, so again, we have electron from the environment, and as soon as an electron from the environment was needed, this entire structure becomes -1. It's a polyatomic ion, all right, which means it cannot have any polarity. It's non-applicable. It's ionic. The whole thing is -1. So therefore, there's no side that's positive, no other side that's negative. Therefore, there's no polarity. Polarity means you have different sides, like a bipolar person. That's normal sometimes, and sometimes not so normal. Okay? All right, so you can make your own guesses about my mental stability another time. Okay, now let's continue. All right, now I have drawn what I think is a pretty good structure, but could I have also drawn another structure? And the answer is yes. Now, before I can draw, I'm going to show you the other structure that you guys possibly could have drawn. Let me do some formal charges, because formal charges help me figure out whether or not my structure is the best possible structure, and it gives me some insights to whether or not the drawn structure is in fact something we can consider. So what we do is we use very simple. We take the valence electrons. In the case of chlorine, there was 7. And I'm going to subtract it by the assigned electrons. Now, the assigned electrons are the electrons I'm using to make the structure work. Sometimes it'll be its own. Sometimes it'll be others. So let's go see it. So we say all of its lone pairs are assigned and half of the bonding. So we say that the chlorine is assigned 7. All right, and 7 minus 7 equals 0. So this tells me the formal charge on the chlorine is 0. What does it tell me? That means that chlorine is using all of its electrons it started with. And by the way, party people, that's a good number. We want to see zeros. When we draw structures and we have a 0 formal charge, it tells me that this chlorine didn't gain any electrons or lose any electrons to make this structure work. Okay, now we do the same thing for the oxygen. Oxygen has 6 valence electrons. That's what you start with, and we're going to subtract its assigned electrons. All right, so we go back to the drawing here, and we see that we consider in the assigned electrons all of the lone pairs, including half of its bonding. And you can see the electrons assigned to the oxygen include 7, 2, 4, 6, 7. Mr. Gronsky, that this electron here, this black triangle, came from the environment. Why is it part of oxygen? Well, it's using it. Again, doesn't matter what's red, black, or blue here. So we would say that the oxygen is using 7 electrons. It started with 6, but it's using 7. Now, 6 minus 7, last time I checked, okay, is equal to -1. And as you can see, this oxygen needed 1 electron extra than what it started with to make this structure work. And if you add the formal charges together, you should get the actual charge of the polyatomic ion. All right. You may say, okay, so what? Well, there could be another structure here. And I'm going to show you the other structure that you possibly could have drawn based on everything I've taught you. Okay, remember, complex structures will have multiple choices. This helps us narrow down the most probable choice. Okay, are there limitations? Yes, electrons are not dots, but we can still get a lot of information out of here. So here's my chlorine. Okay, what I'm going to say is I'm going to start with my 7 valence electrons. And put out the oxygen's electrons, and it has 6. All right, 1, 2, 3, 4, 5, 6. And then I'm going to put out that black triangle to show that that is needed. But now what I'm going to do is I'm going to make a double bond. Okay, and I'm going to make a double bond between the two. Now, why would I want to do a double bond between the two? Well, from last night's homework, it should be obvious that oxygen loves to have a double bond. Oxygen has that 1s2, 2s2, 2p4. So it wants to gain 2 more electrons to fill those p's. So oxygen wants to have a double bond if it can. So my friends, in chemistry, what I do is I'm going to put a double bond here, and I move these dots here. And the reason why I'm moving these dots for the oxygen is that oxygen still has to follow the octet rule. Okay, so that's how I do that. If I was to move them for the chlorine, oxygen would wind up having more than 8 electrons surrounding it, and that can't happen. It's a row 2 element. It can only have 8 total. So it has 6 gaining, or feeling like it gains 2 more with a double bond will make it feel like it has 8 like a noble gas. Okay, now this is a possible structure because oxygen likes a double bond, and chlorine, you say, Mr. Grodsky, chlorine is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Chlorine feels like it has 10. Well, chlorine is a row 3 element. It has a possibility of going beyond the 8 because of the D sublevels it has. It could be an expanded octet, so this is a possibility. But before we get started, let's not forget that we added an electron from the environment, so the whole thing is -1. And we also have to keep in mind that formal charges will help us figure out if this is the better structure than this. So let's go to it. Let's go back to formal charges. So we have 7 valence electrons minus the ones that are assigned. Well, what's assigned to the chlorine in this case? Again, you could probably see it without me doing this, but I think it makes things clear. All of the lone pairs are assigned to the chlorine, plus what? Half of its bonding. Okay, so if you notice, 2, 4, 6, 8. And what does that really mean? It started with 7. Can you clearly see that it has it's using 1 more electron than it started with to make this work? Yeah. So 7 minus 8, okay, is going to equal -1. So this chlorine, to make this structure work in our dot diagram, okay, needs 1 more electron. Needs 1 more electron than it started with. So the formal charge on it is -1. It's not an oxidation state, guys. It just tells me it has 1 more electron than normal to make this work. It used 1 from somebody else. Okay, oxygen, okay, starts out with 6 valence electrons. And we're going to subtract its assigned. All right, and what is its assigned? Well, it's going to be half its bonding, so right there, and all of its rest of its lone pairs. So I get 1, 2, 3, 4, 5, 6. 6 minus 6 gives me that 0. So the formal charge of oxygen is 0. Like we said, oxygen wants a formal charge of 0. 0 is the best number. Okay, you notice if you add these together, we get the charge of the polyatomic ion, which is still tells us that this could be a possibility. Now, between these two possible structures that you could have drawn, thinking that chlorine can have an expanded octet, which is certainly a possibility in row 3, this structure is not the best structure. Why? Well, if you look very carefully, maybe not that carefully, the -1 is on the chlorine. And the other structure, the -1 was on the oxygen. So what we say here is that if you're going to have negative numbers, and negative numbers tell me that compounds are gaining an electron from another element to make this happen, it would make sense that the -1 would be on the most electronegative element. So if you have to have negatives, the negatives should be on the most electronegative atom. And you should know that oxygen, being in row 2, closer to fluorine, is more electronegative than chlorine. It has a higher effective nuclear charge. So it has the greatest possibility of gaining electron. So this is the one, this structure, okay, is the most favorable. This is not, because you're saying that chlorine would have to gain one to make this work, when oxygen is the one that would do the gaining between the two because it is more electronegative. Okay? Now, you may not have drawn this structure, but it's still good to know this, okay, because you may have. All right? You have to evaluate structures this way. Okay, now that we have all that done, we can figure out the electron domain geometry, which is pretty simple here. When you have two atoms, it can only be linear. There's no other way to put two things together. Okay, here and here, here and here, it's going to be linear. The molecular geometry, also linear. The hybridization, okay, and they may say, well, if it's linear, it's sp hybridized. And I guess I could accept that, but do I need to have hybridization? Remember, hybridization is nothing more than a theory to help us explain what we have. Could I explain the bond between chlorine and oxygen without hybridization? Well, yes. Think about chlorine for a second. Chlorine is going to be, okay, unhybridized P's on the outside. Here's my P Y. Here's my PX. And then PZ jumps at you and goes into the board. Don't forget you have the S orbital, which, by the way, would be about the same size. And, of course, its valence electron and the unhybridized P here is going to overlap an unhybridized P orbital from an oxygen. Because both of these are bonding only on one side, I can use unhybridized P's to explain the bonding of each. It's only when we have a central atom that bonds to multiple things in different directions do we need to have hybridization. So my friends, this is just a sigma bond between unhybridized P's. So anytime I have terminal endings, this bonds on one side, and you should know this, party people. Once you bond to one p orbital, these p's are now filled, and now you can't bond to the other side. And of course, that's what happens here. Okay, so we do not need hybridization to explain this. Now, if you want to say SP, okay, I can't take it away from you, but you can say none as well. All right, bond angles are 180 degrees. All right. All right, it's going to get a little more complicated, and we're going to need formal charges as we continue. So let's continue on to ClO2 negative. Now, if you have any questions, please tell Matt to text me. All right, as my phone is dying. All right. So, Brady, can you get the charger for my phone and plug it in over here? The charger is by the living room there. All right, so let's continue on to the ClO2. Now, this was the hypochlorite ion. Remember, we had low number of O's. It's the ite, but this is the lowest number. So this is the hypochlorite ion. And the next one we're going to work on is the chloride ion. It's not there. Okay, how about in the bedroom? You go to the bedroom in the east wing, across from the pool and the indoor archery. Okay, take the Segway. Okay, it's gonna take you forever. Yeah, right. Sure. Okay. Okay. Boy, that Segway's fast. All right, cool. All right. Are you hungry? The butler will cook you something. Which cook would you like? Would you like an Italian cook to cook for you, or the Polish chef? We only have 2 on staff today.
What?
Forget it. You want homemade kielbasa? All right, we can do that.
Not one.
Yeah, okay. All right. So moving forward, ClO3. We'll start this one, and I think you guys are going to have a break soon. All right. So here we go. ClO2 negative. So this is the chloride ion. All right. Let's get rid of this stuff here, maybe. And let's get started. Okay. So Cl. I have Cl and I have 2 O's. All right. I'm going to put the O's on either side. Why? Because I'm just trying it. It's trial and error. I'm going to put out the valence electrons for the oxygens. And I know I'm for the chlorine first. It's central atom. Now, how I know chlorine's a central atom? Just by pretty much the first one given, it kind of always tells the tale of the central atom. Normally, the first element is a central atom. But I know that oxygen, most of the time, is terminal. Okay. In any case, the one with the greatest number of electrons sometimes can cause the central atoms as well. Again, it's mostly trial and error and experience. But in any case, here's chlorine with its 7. So 1, 2, 3, 4, 5, 6, and 7. And then the oxygen has 6 valence electrons, so I draw that out here as well. And I draw this one as well. Okay. Now, I can see by evaluating that this oxygen has its 8. It's a row 2 element, so it's bound by the octet rule, so that's stable. Chlorine here, or this oxygen, I'm sorry, has, okay, this one right here, the right one, has 7. And the middle chlorine has 7. So clearly, we're going to need another electron from the environment. So an environment's electron, this is it gains another electron, okay, to make this structure work. And that makes sense because that's a -1 charge out there. Now, some people will teach you, put out all the valence electrons and just put them around. I like to use the valence electrons of the structures and do this first. It doesn't matter. So let's get rid of this. But right now I know that this thing, the whole thing is -1 because it gained an electron. All right. And let's see if this makes sense. Is this the best possible structure for this atom or this polyatomic ion? So we go to formal charges. So I have 6 valence electrons minus the assigned electrons that I needed to draw this. Okay. And I go with my green and I say all of the lone pairs for the oxygen and half of its bonding. Okay. So if you notice, that's 7. This oxygen needed 1 electron from somebody else to make this structure work. So clearly, party people, this is -1 structure for oxygen. Okay, now chlorine, okay, let's do chlorine. It has 7 valence electrons, and we're going to subtract its valence. I'm sorry, it's assigned. So 7 valence electrons, those are electrons it brought to the party. And how much is it going to use? Okay, well, it's all of its lone pairs, half of its bonding, and it's using 1, 2, 3, 4, 5, 6. 7 minus 6 equals what? +1. So we'd say chlorine is +1. And if you notice, there is a problem with this structure already. Okay, we'll kind of let you think about that. All right. And yeah, Brendan, you're right. There is something wrong with the chlorine. I know you were thinking that. Okay. Okay, cool. All right, now, so this guy is +1. Do the oxygen, okay? The oxygen has 6 valence electrons minus its assigned. And the assigned electrons here are going to be 2, 4, 6, and then half of its bonding, so 7. All right. So 6 minus 7 In this case, 1, 2, 3, 4, 5, 6, 7. So this gives me a -1. All right. All right. So I was incorrect, as Brennan was, that there isn't really a problem here. I thought I was thinking incorrectly. Chlorine has a +1. Oxygen has a -1. Oxygen has a -1. So the collective charges of your formal charges equals a -1, which makes sense. -1 plus a +1 plus a -1 is a -1. So that shows you that you're onto something. But the question is, party people, do I have the best structure possible? Okay. Now, you may say, well, Mr. Grotsky, the negative is on the oxygen, so that makes sense compared to what you did on the first one that we talked about. Sure. The -1 on the first one means that what? Means that I have gained an electron from the other element, or in this case, the environment right here, to make this work. And since oxygen is more electronegative, that would mean that this is a reasonable structure. But what if I could get my oxygens to be 0? Remember, we talked about this. A 0 structure is a more preferred structure because it means that you're using all of the electrons. If I'm drawing these Lewis dot diagrams and I'm getting positive ones and negative ones, it means that I'm using, if it's negative, someone else's electron to make this work. In the case of chlorine, I'm using what? I had to give up an electron, right? +1 means I lost an electron to make this work. And this is troubling to me that chlorine is losing one and oxygen's gaining one. Anytime you have electrons being passed around to make structures work, makes them improbable. All right, so I'm going to draw this another way. Okay, I'm going to draw this another way. I'm going to put, and I think the bell is just rung, so I'm going to pause here and we'll get back to you. So take a break. All right, and I'm going to pick up in about 4 minutes. All right. Cool.
That over here. Daddy, look. I'm cutting all her hair off.
Oh yeah, cool.
We just have this part. Good. Good, she's good. There's. Evie stepped around and stepped around. Blue hair again. Look, she only has this much hair. This much hair is all of it only, so I'm cutting more hair.
Okay.
Make it like you. See how much hair she has? She has little hair.
Cool.
She only has a little bit of hair, so I'm cutting more hair. Be there.
It's your voice, kid.
My hair.
No.
You don't hear anything.
Well, eventually you will, okay? Don't worry. Back to where you were.
You don't hear anything. You're just joking that you hear something. Like, should I buzz her or her hair off? We need a buzzer.
Go for it, kid.
What?
Go for it.
I'm not picking you. I'm picking that person. Like this guy? Like this person? Cool. Like this person. Woohoo, woohoo.
All right, so I'm going to get started here. All right. And I'm assuming our break is over. And I'm not going to go the entire period here, guys. I'm going to finish this worksheet out. I'm going to go a little faster as we continue on here. Just wait and make sure. Okay, Devin needs another minute. All right. All right. No, Brady, you cannot feed the elephants, yeah. Okay. The zookeeper has to feed our animals first, okay? So we can't do that. Yeah. All right. The zookeeper is late today, I know, so don't go into our personal zoo. The giraffes are hungry. The lions are hungry. Okay, let's continue. All right. All right, so here we go. So we left off with our one possible structure for the chloride ion. So let's continue on because this is exciting stuff. All right. And I'll tell you, my 4-year-old's learning a lot of chemistry this morning. He already knew this. Any case, so let's start this another way. So let's do oxygen over here again. And we have our chlorine in the middle. All right. And another oxygen. And this time, what I'm going to do, because like I said before, oxygen loves double bonds, because a double bonded oxygen will give me a formal charge of 0, like we did in this structure here. So that's what I'm going to do. So putting out the valence electrons, I'm going to do 2 lone pairs here. I'm going to bring a lone pair here. That's my 6. Chlorine, okay, is going to have 2 pairs here. And we'll just try this for size. All right, and then we'll do a dot here, and then we have that red triangle. All right, and we have a red triangle there, and we have 1, 2, 3, 4, 5, and 6. I guess I can move that over. All right. Okay. Now, what do we have? Well, making a double bond is going to change some things up, making sure I have the right number of valence electrons. I can clearly see that in this structure, I have 6. Oops, that didn't work so well. I'm going to move that over here. All right, I have to. I don't know what I'm doing here. Okay. It's like I'm stuck here. Last time I used that function. Okay. All right. Give me a second or I lose my. Yeah, it didn't like that, did it? Let's see. Looks like I'm all hung up here. Oh, this stinks. Oh, I'm stuck. Give me a second here. Oh, what's going on? Come on, here we go. All right, back in business. So here we go. So counting our formal charges here, very simply, I have half of my bonding, and let's do it another way. Do it another way here. Half of my bonding. Okay, and you can see by doing this, I got 6 minus 6. It gives me a formal charge of 0, and that's a 0. And the other way, we have a formal charge here of the chlorine, half of its bonding. And what we have here is 7, okay, minus, well, guess what? 1, 2, 3, 4, 5, 6, 7. Nice. Okay, that's going to give me another 0. I'm liking this because I'm in a scenario where the elements are using their own electrons they bring to the table for this structure. There's no giving one like over here or losing one. This oxygen, okay, half of its, all of its valence electrons is 6 minus, okay, what it would be for its assigned electrons, and that would be half its bonding and all its lone pairs. You can see that's going to be 7. And that's going to give me 6 minus 7, -1. Okay, let's move this orange juice. That was just freshly squeezed from oranges from Costa Rica. Okay, -1. And what we have is a -1. And as you can see, this polyatomic ion in brackets totally equals -1. Now, I hope that you can see that this is a very, very probable structure. Now you may say, well, why? Well, first of all, instead of +1 and -1, -1 and +1, I've got zeros for elements. That means that's more probable. Isn't it more probable that the structure that these guys make or what they start with, when you have to start passing electrons around, it's probably not going to happen. So this is the best, most probable structure. So I like this structure. But either way, the -1 would go on what? The -1 would have to go on the more electronegative element. Now you may say, Mr. Grossi, why don't we put a double bond on the other oxygen? Well, if we were to put a double bond on the other oxygen, this would make this negative, but it would wind up making the chlorine -1. So if we were to make another double bond and move these two dots over here, this oxygen would go to 0, but this chlorine would go to -1, and that wouldn't make sense. The more electronegative element is the one that gained the electron. Okay? So it makes sense that this is the most probable structure. I have two elements that are 0, which means they used exactly what was given to them, and the one that had to do the gaining, someone has to gain electron from the environment, is the more electronegative atom. So this is the best structure, and this first structure is not. And you can see the power of formal charges. They lead you the way. Now, I'm going to redraw this to answer our questions, because we're going to answer questions about molecular geometry, electron domain geometry, and those kind of things. So here's what I have. So let me just redraw this. I have chlorine with what? 2 lone pairs. And I'm just going to draw it like this to remind myself the structure. I've got a double bonded to the O. All right. 2 an oxygen that has what? 6 lone pairs. This whole thing is -1 charged. And this gives me more insight to the structure. Now, you notice I drew it in this shape because I know that I have some lone pairs. Before I go there, though, does anyone figure out, can anyone tell me if, in fact, I am finished drawing this structure? Correct, Devin. You're absolutely right. Okay, Devin is right. All right, you have to draw another structure. Okay, why is he right? Well, if I've got a double bond on one side, why couldn't I have it on this side? So we have resonance here, party people. We'd have another structure we would have to write. So lone pair is on top, double bond, but be careful. If the double bond is on this side, you're going to have only 2 lone pairs of electrons to make that happen. Single bond for this O on this side, that would mean you have 3 lone pairs. And we would draw brackets to show the entire thing is -1. Obviously, it cannot be polar or nonpolar. The whole thing is -1. And that is the correct Lewis dot diagram for the chloride ion. All right, a lot of fun there. And again, you had to be driven by formal charges to see what the best structure is. And this is the best structure. I've got more zeros, and the negative is on the more electronegative atom. Now, again, we have limitations. We have limitations, and I'm going to get to that maybe at the end. There are limitations in this, but it helps us get these structures, which we accept as the known structures for the chloride ion. Now, answering some questions here. The electron domain geometry. Well, if you look at the lone pairs, here's 1, 2, 3, 4. Okay, well, if you've got 4 lone pairs, then the geometry where electrons are is the tetrahedral. And if you have 4 lone pairs, but there's only atoms at the legs of the tetrahedral, considering what is the shape of where the atoms are, that's called the molecular geometry, what would we call this? Correct, Mira. I know you were thinking it. All right. But next time I want you to scream it. Okay. So yeah, this would be bent. All right. Right. In the tetrahedral family, if you just have 2 atoms on the legs of the tetrahedral, these 2 lone pair make this shape bent. So the molecular geometry is bent, electron domain geometry is tetrahedral. The bond angles, we would say 109.5, but we know better. I would accept this, but these 2 lone pairs actually bend this into more of a 107 area, but we'll take 109.5. And the hybridization. Obviously, if you're in a tetrahedral family and you have 1, 2, 3, 4 pairs of electrons, okay, then it must have been an S and 3 P's come together. So this is sp3 hybridization. And the bond angle is 109.5, but less than that, as we talked about. And of course, polarity is non-applicable. Okay, so yeah, It doesn't get any harder than these types. I'm giving you the ones that require the most, these are the most challenging Lewis dot diagrams that exist in all of chemistry, absolutely, okay? But you need to understand resonance, and you need to understand what, okay? Formal charges points you the direction of the best structure, okay? Hopefully you're seeing this is not so bad, okay? Looking for any questions you might have. Matt will lead the way. If I have lost you, 7. All right. And it looks like no one has any questions. I know that we're on a delay a little bit. So we're going to move on to the number 3. All right. I'm going to make some room here and get rid of this extra material. And by the way, this video that I'm making will be posted. I'm sure you want to go home and listen to the entire hour, okay, because that's what you want to do. All right. So let's do ClO3. And this will be the last one we'll do together. And I'll let you do the other one for work at home or in classwork. Okay, we'll leave it at that. Okay, so number 3, ClO3 negative. All right. So I got my chlorine, and I'm going to throw 3 O's around. I'm guessing it may look like this, but I may not. Remember, it's trial and error. I put out the valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay. Oxygen has 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And I do the same with the other oxygen. By the way, this is a ClO with a lot of O's. This is an 8. So these guys are 8s. This is the chlorate, and this is the 8 with the most. This is the perchichlorate. Perch means a lot more. Okay, isn't that special? Okay. I haven't lost you guys yet. Awesome, awesome sauce. All right, so we're just going to kind of finish this one out, or at least get you started. Okay, so I've got 1 bond with each of these oxygens. All right, and that's a good possibility. It's nice and stable. The oxygen's a terminal, and the oxygens are stable with their octets. They're a second row element. The chlorine has 7. That's at least wants to have 8, so we're going to add a red triangle to show that that gained an electron from its environment. So in its simplistic terms, this is -1, okay? Now, have some issues here. Let's do the formal charges, but now I'm going to pick up the pace here because I think it's getting easier. Each oxygen is, the way that I've written, is the same. So I took 6 valence electrons. I'm going to minus the assigned. Well, I hope you can see that the assigned is going to be what? The assigned is going to be half its bonding. So it's 7. So according to my diagram, 6 minus 7 is -1. So I'm going to have a -1 on all of my oxygens. Whoa. If you think with me, if I'm having a -1 with all of my oxygens, what charge must the chlorine be to make this work? It's got to be a big positive. Well, if you notice, each oxygen, okay, is taking 1 away to make it work. So this chlorine's losing 3. But if you still don't see it, and this is good, we have 7 valence electrons for the chlorine, minus what? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the chlorine, okay, is going to be a +2. Now, why is it +2? It gave away 3, but also what? Took in 1 from the environment. Remember, the +2 means it's losing a total of 2 electrons to other elements to make this work. Does that sound good? Does that sound like a possibility that chlorine's going to lose 2 to make this work? Remember, the best structure is the one we have zeros, meaning whatever you bring to the table, you use. So this is probably not going to be a good structure. Yes, the formal charge is equal to -1, but not the best structure. Okay, So let's try another structure. And now I'm going to make sense of this. I see chlorine has 4 pairs of electrons. Okay? And notice there's 2 lone pairs here. So in any case, I'm not sure if this is the way to do it, but I'm going to make a double bond occur. Okay? So I've got my chlorine, and I've got a chlorine here. What I'm going to do with this oxygen is I'm going to make a double bond. Now, I just guessing. You know, it's not like I know exactly what this is. I'm guessing, but I know O wants to go to 0. So I'm going to make another double bond to this one. That means it leaves me with 2 lone pairs left. It satisfies oxygen's octet. I'm going to leave everything else alone for right now. Okay, I've got a single bond here. 2, 4, 6 over here with that red triangle. Again, the shape isn't correct yet. We'll make all those adjustments at a later time. This oxygen has just what? A single bond. We'll just leave it that for now. And this oxygen up here has single bonds. Okay. And then let's evaluate our formal charges. We're real quickly, this is going to be a 0. This oxygen will have a formal charge. It has 6 valence electrons and half of its bonding, right? Again, you don't have to draw this, but I'm just helping those that are still quite not seeing it, but this is using all of its electrons. So this oxygen is 0. This oxygen up here is going to be what? Still -1. This oxygen went to the market. This little piggy, no, you get, so this oxygen here is also going to be -1 for the same reasons we talked about over here. But this chlorine now, this chlorine is now just lost 1. So this chlorine, if you think with me now, has 1, 2, 3, 4, 5, 6, starts with 7. 7 minus 6 is now +1. All right, this is getting better. Now it just lost 1. Okay, you can say, okay, cool. So a double bond definitely helps the structure because now I'm getting, I have a 0 somewhere. Could I get another 0? The question is, could I improve this even more? And the answer is yes. Because right now I have a double bond here making a 0, but I still have a +1, -1. That means what? Someone is gaining electron from another element, someone's losing. I can make these both go to 0 if I do what? Yeah, if I add another double bond. So what I'm going to do is erase this, and I'm going to put another double bond here. Okay, so let me just erase this. Okay, oops. And put another oxygen here. And this oxygen is going to put out a pair, 2 lone pairs left. Chlorine puts out its other 2 here. So 1, 2, 3, 4, 5, 6, 7. Okay, good. So now if I check out this oxygen's formal charge, half of its bonding, okay, which is going to make it 6 assigned electrons and 6 valence. This is going to be a 0. Cool, that's better for oxygen. That means it's using its own. And then we evaluate the chlorine, half of its bonding and its lone pairs. What do you get? 1, 2, 3, 4, 5, 6, 7. 7 minus 7 for the chlorine gives me a 0. And you can clearly see by using formal charges, I have directed my way to notice that this structure, okay, is a chlorine that double bonds to this O, double bonds to this O, it's single bonds to this O, leaving the negative on the more electronegative atom. So we are left with a structure that looks like this. And let me just clean this up. And I'm almost done, party people. All right, it leaves me with this structure. Chlorine double bonding to an O. Make sure you have the right number of free electrons. Double bonding to this O leaving 2 lone pairs, single bonding to this O, all right, leaving 6 lone pairs, but, okay, I have a lone pair here. So I probably want to rearrange this again to make some sense of it. So this is what I'm going to do. I'm going to put a Cl here, 2 lone pairs here. I have what? A double bond to the O here. Another double bond here. And again, I can put them anywhere I want. I know there's going to be 2 of them. Right number of lone electrons. And then a single bond to the O. I'm doing this so I get a better sense of this shape. Okay, this lone pair is going to arrange itself into this shape. And this is my best Lewis structure. Don't forget, you had to what? Gain an electron to make this work. So this is a -1. My question to you, is this the only structure possible? If I have 2 what? Double bonds, who's to say the double bond's not over here? Who's to say the 2 double bonds aren't on this side or this side? So you should be able to see that there are more structures to draw. And I'm going to leave you to draw those structures. Okay? And I'll just help you answer the last couple of questions. Hybridization. Well, count the lone pairs. 1, 2, 3, 4. I'm counting the lone pair, and I'm also counting one of the sigma bonds. There's a 4 here. So this would have to be sp3. Okay? And I'm going to leave you with the shape. The shape electron domain geometry is tetrahedral, believe it or not. Also, what's the geometry, the atom geometry? So electron domain geometry is tetrahedral for 4 pairs of electrons. We only consider the 1 sigma bonds. The geometry of where the atoms are is the top of a 3-sided pyramid. And that's the what called the Trigonal Pyramidal or Trigonal Pyramidal. Trigonal Pyramidal is a shape in the sp3 family. The bond angles are, because it's a tetrahedral family, are 109.5 degrees, but you can use less because this is going to strain on all the bonds. All right. And the bond, the polarity, of course, doesn't make any sense because it's an ion. All right. But I want you to draw the other structures. It does have resonance. Okay. Just by alternating where the double bonds are. And for homework or classwork, I want you to try the perchlorate ion. Okay. And that's it for today. And I hope that sheds some light on these more difficult structures. Okay, let me just get a question here. Okay. Oh, okay. So Devin has a question about drawing the resonance structure with the dotted lines. If you draw them with dotted lines, it's almost impossible to draw the right number of electrons, because then you would have electrons that are going back and forth from having, in case of oxygen, 6 electrons or 4. So that's a great point. When you draw dotted lines, it's hard to do that. Normally, the dotted line is a way to understand it. So some people will do the dotted lines. It's hard to do. If you're doing dotted lines, okay, for that extra bond that goes through all of them, then you might have, okay, dark ones and then very light empty circles. But that's just, normally it's written this way without the dotted lines. Tough to make sense of that. Okay, so you're going to finish out the resonance structures and then try number 4 on your own. Check the key. That's all for today, unless there is more questions. Hopefully you pick something out of this. So the homework would just be to complete number 4. Okay, and I will post these videos if you want to review them on your own. The polarity of number 2, as someone asked me, is none. None applicable. They're all ions. Ions don't have any polarity. The entire structure is -1. That's it. Have a great day. Finish out this worksheet. Look over the key. Thanks for playing with me today.